This is Jack Jackson. In this video we're going to be talking about the negative binomial distribution. This is a generalization of the geometric distribution. Remember that in a geometric distribution what we do is we have independent Bernoulli trials all with the same probability P of a success each time, and the probability of failure of course is 1 minus P. So in this case probability of success is 1/3, failure is 2/3. And what we do is we repeat this experiment until we get our first success, and we count the number of trials. So we could get a success the first time that has a probability of 1/3, and we let x be 1 because it took us one try to get that. At that point the experiment's over and the tree stops. If we get a failure the first time, then we get our success the second time. Notice we had a probability of failure the first Q and a success P the next time, so we get a probability that happens is P times Q. But if we get a failure, of course, then we stop. If we get 2 failures, then we go again, and so forth. So this tree actually goes on forever, and we obtain this. Now, in a negative binomial distribution, it's a very similar situation. It's a generalization of this, actually, of the geometric. So what we do here is we again perform independent Bernoulli trials, each with probability of success is P and a probability of failure is 1 minus P, which is Q. But we're going to find K successes. In this example I've got illustrated, we're looking for 2 successes. So we know that second success is going to come on the last try, because we're going to, once we get that second success, we're going to stop. And then this time, however, instead of counting the total number of trials, we're going to count just the number of failures. So let's look at this top branch of our tree. We could have a success. No matter what we do the first time, we're going to go again because there's no way to get 2 successes with 1 trial. But we could go 2 trials and get a success. Well, that's going to happen with a probability. So first of all, that's going to be x equals 0 because there's 0 successes. And that's going to have a probability P squared. This particular example I've got P equals 0.1, but P could be anything. So that's probability of P squared. Now what if we got a success first, then we got a failure? Well, then we're going to go again. If we get a success the next time, notice that we have 1 failure and 2 successes. The experiment's over. X is 1 failure, so X is 1. And the probability that that particular pattern, success, failure, success, happen, notice we have two successes and we have 1 failure. Well, what about the next time? The next time, when we come down here, we could get, what if we got a success, failure, then another failure, then we could get a success. Well, that's still a total of 2 successes, so that we stop, and notice we're going to get 2 successes again. So notice every time we're going to get a probability of P squared. But how many failures did we have? Well, we had 2 failures, so that means X is 2, and we're going to get a Q squared there because there are 2 failures. Okay? If we're on this branch here, it just keeps going forever. Let's look down here. Failure, success, success. That's going to get x equals 1 failure. And just like up here when x is 1, we're going to get a P squared. And we're going to get 1 failure. Here we had 2 failures. And of course 2 successes. Always 2 successes. X counts the failures, so x is 2 on that branch. These other branches, they keep going. Here's one where we did failure, failure, success, success. So that's 2 successes, 2 failures, and so x is 2. And this continues on. Okay, let's see if we can figure out what the probability for a particular x is going to be. Well, you notice that every time we're going to get 2 successes, and then we're going to get x failures. However, notice that when x is 1, that happened more than once. And when x is 2, that happens more than once. Okay. And perhaps some other places. So how many times is this going to happen? Well, we need to count up these things, and we can use our counting arguments. That's going to be a binomial coefficient or a combination. How many are we going to have? Well, it's really a matter of where we place those successes, or where we place those failures. Let's think about where we place those failures. They're going to be, one way to think of it is where we place the failures, and they're going to be X failures. But where can we put them? Well, how many branches do we have here along our path? Well, notice that we have X plus 2 edges along our path. However, one of those cannot be a failure, so we can subtract that. Now we want to generalize this, so what we get is, instead of this being 2, suppose it's just some number k, then we're going to have k successes, that's going to be p on k of the edges, and we're going to have x failures, so that's going to be x of the failures will be, well, each one will have probability q, so there's kp's and xq's. And we're going to choose where we're going to place those x failures, and they're x plus r minus 1. Okay. Now, by the symmetry of this, another way to write this part right here is x plus r minus 1. We can say where we can count how many places where we put the r minus 1 successes, and we'd rather write it that way. But I'm going to choose to write it this way. So here is our probability density function. Now I'm going to switch over to Excel, and here I've got it actually listed with the formula r minus 1 there, rather than with x. But symmetry, it doesn't matter. So you got x plus r minus 1, and you got r minus 1, or you could put x here. It doesn't matter. Get the same number. And we have r p's and x q's. And so that's your formula for the PDF. So notice this gives us a family of distributions. And so let's review. In a negative binomial distribution, we perform an indeterminate number of independent Bernoulli trials, each with the same probability of success, p, until a fixed number, r, successes occur. Let x be the number of failures until the rth success. Notice that the negative binomial distribution is a generalization of the geometric distribution. If r equals 1, then the negative binomial is more or less the same as a geometric distribution, except that in the geometric distribution, the random variable counts the total number of trials, whereas here in the negative binomial distribution, the random variable x counts the number of failures. The two defining parameters are r and p, and they have the blue backgrounds here, and red text there, red font. And so those are the two numbers we can change. So in this particular one, I'm looking for 4 successes, and I want the probability of success on each trial is 0.7. Well, notice that the Excel spreadsheet, the formula here is 1 minus C7. C7 is the P, so when I subtract that, that'll give me Q. It turns out that, without proving this now, I'm just going to tell you what some of the parameters are. The mean turns out to be R times Q over P. And of course you can see that I used that formula here. I did C6, which is R, times C8, which is Q, and divided by C7, which is P. And so that figures that out. It turns out that the variance is RQ over P squared, and so I use that formula. Of course, RQ over P is just the mean, so it's just the mean divided by P. That's another way to say it. And that's actually what I did here. I took the mean, C9, and divided by P, which was C7. Standard deviation, of course, is just the square root of the variance. That's the square root of C10. And it turns out that the skewness is 1 plus P over the square root of PR. And I use that formula here. 1 plus C7 in parentheses divided by square root of C7, which is P, times C6, which is R. And so you can see that I use these formulas to compute these values. Now over here I use the formula, and you know what, this is in a percent form. I think I'd rather have this just a decimal form, so I'm going to change that. I'm going to go back here and just change it to a number format. And we'll go ahead and show some more decimal places. And so this is the values of the PDF. And notice there is a negative binomial distribution built into Excel, and so I use that. Of course, the way to do that is you go to FX here, and I'm going to look at statistical formulas. I'm going to look up negative binomial. Notice there are a whole bunch of things here. Some of these we'll get to this semester and some we won't. Negative binomial. Okay. So we have number of failures that you're looking for, which is our X value. Number of successes we're looking for, that's our K value. That's going to be fixed ahead of time. The number F is our random variable. The probability of success each time, that's our P. And cumulative is true or false. If you do true, it's going to be a CDF, and false is a PDF. If I click on this, it actually comes up here, and you can actually enter in your numbers here in the wizard, and it kind of tells you what it is. Okay, so if you notice, that's what I used here. So this says always look to the left at E11, which is our X value for the first parameter. It says C6. Notice I put dollar signs because I want to copy and paste this when I made this. And C6 is the R, the number of successes. Next will be the number of failures. I'm sorry, it's going to be the probability of success. That's P. That should be right here, C7. Okay, and then actually I could actually enter that with a true after it, a false after it, and that would give me make sure it was a PDF. Over here, I actually could have done it a different way. I could have taken this and taken this same formula but added a true at the end, comma true inside there, and it would have worked out the CDF. But I can also do the CDF as you can do any CDF. Take the first one equal to here, and this next one is the one above plus the one to the left, and then copy that so it's always one above plus one to the left, which is exactly what a cumulative distribution is doing, so that this number here then becomes the sum of all these up to that point. So in any event, I have this worked out. Now this goes on forever, so my table only goes down through 29. Okay, but in theory the table goes on forever. But at some point we're so close to this that it's hard to tell the difference. I'm going to go ahead and change this to a decimal number 2. And we see that we're almost at 1 there, and not quite. It does go on forever. Now over here we have the graphs of this, and so here we see our negative binomial distribution. And what typically happens with a negative binomial distribution is you get some, maybe some fairly tall bars, and it goes up a little bit and then pretty quickly starts dropping down. And so this one is skewed to the right a bit. Here's the graph of the CDF. As with all CDFs, it starts at 0 here, and then which it didn't have a dot here, but there would be 1 at 0 here. It's actually 0 all the way up to this point right here, all the way up to 0 actually. And there should be a dot there, and then it goes on up from there. Now in fact, the negative binomial is really, for the CDF, is always just a step function, so it's really just a little line segment going from here over, open dot, up here, steps up, goes straight over until it gets to this dot, straight up. Not connected straight up, just a jump, a step, and it's straight over, horizontal line segment. So a bunch of little bitty horizontal line segments, but the start of those horizontal line segments are the dots that you see there, and you get the basic idea that it's going up and then leveling out. So that's a negative binomial distribution, and that is a generalization of the geometric distribution. By the way, this particular spreadsheet goes over several different things in discrete distributions. This goes over some basic counting techniques that we covered in an earlier section, and starting down here with the number of ways of ordering or permuting indistinct objects, which would be n factorial. This is factorial is FACT in Excel, and so it's based on this number n, which is C4. So this should be factorial of C4. So C4 was 20 at the moment. I can change it. Let's say 15. Everything is changed accordingly. So this is 15 factorial. Of course, this e plus 12 means times 10 to the 12th. As we discussed earlier, these things get rather large rather quickly. Now, there were 4 different things where we're trying to find number of selections or arrangements, and we had sort of 2 different criteria, whether we're finding number of arrangements or number of selections. Number of arrangements is where the order matters, and number of selections is where the order does not matter. Okay? And then we had 2 other options where the repeats could be allowed. So for example, that could be done without replacement, and repeats are not allowed. Or repeats are allowed, that's done with replacement. And some examples, if you have k officers chosen from n, and 1 office per person, that's n permute k, which is n factorial over n minus k factorial, or in Excel, PERMUT. And then we're C4 and C5 are n and k. So that's what the formula is right there. The formula here, if the order matters, but we do allow replacements, it's just n each time, and there are k of them, so it's n to the k power, which is C4 to the power C5. And if we have a committee of size k chosen from n choices, that's n choose k, written one of these 2 ways usually. That's not right. N factorial over n minus k factorial, and it's also divided by k factorial. That's called, in Excel, that's a combination, C-O-M-B-I-N. And that's C4 is where n is, and C5 is where k is. N choose k. And you can see with the value of that. And here we have the ways of ordering k things where, not ordering, of placing an order for k meals with n choices of meals. So we're selecting k things. Maybe I should say, instead of ordering, because it makes it sound like they're in order, because they're not in order. Selecting k meals with n choices of meal. It's n plus k minus 1, choose k. And we discussed this earlier in an earlier video, but here is a spreadsheet that can calculate all of these things sort of at once, all these different options when you just plug in n and k here. Another problem that's kind of interesting is this one. What's the probability that in a group of n people, no two people have the same birthday, the month and day, not the year? Well, this actually turns out to be a very interesting problem and has a sort of counterintuitive answer. At what level do you think it takes it before the probability becomes a half? Well, it turns out that if February 29th is as likely as any other day, and all days are equally likely, there's 366 days a year, and if they're all equally likely, then what we do is we take 366 choose n, divide it by 366 to the n power, and that's the probability that note that they're all different. Okay, and we want to subtract that for 1 to find the probability that we get at least 2 the same. If February 29th didn't exist, there'd be 365 days. So the true probability is maybe somewhere in between. We also have, every day is not exactly equally likely, as we've kind of discussed earlier and back in Unit 1. But this gives you a rough estimate. So each line on this, somewhere around one of these two numbers, that's going to be approximately what the probability is. And something is kind of counterintuitive. It only takes 23 people in a room for there to be a better than 50% chance that they're going to have the same birthday. And from there it gets up pretty big. So notice by the time you get down to, say 32 people, there's a better than 75% chance that they're going to have at least 2 people with the same birthday. Pretty interesting problem there. The next one here talks about a finite distribution, and it takes a finite distribution, which you can change these numbers here. This particular one's just for one with 5 points, and this will compute the CDF. Also assumes these are in increasing order for the x's. Then it'll do the CDF, and then it will also step by step show all the calculations for computing the mean, the variance, standard deviation, and the skewness for that finite distribution. And it shows a graph. The graph will work right as long as these are sort of evenly spaced out. If these aren't evenly spaced out, the graph doesn't work exactly right on this sheet, but it works well for this example. There's a Bernoulli distribution where either you get a success or failure, and we'll call a failure 0 and a success 1, and you can change the probability of success here. And pretty straightforward there, pretty easy distribution. A binomial distribution, and this goes through and computes all of those probabilities for a binomial distribution. Now, a binomial distribution is defined between 0 and n. 7 trials here, and the probability of success each time is 0.23076, whatever. I can change this. Say 0.4 for the probability of the success, and let's say that there are 10. 0.4, and then let's say we have 10 trials, and we want to count the number of successes in 10 trials. Notice that this already computed the probability of a failure, the mean, the variance, standard deviation, and the skewness, and it makes out the table. Now at some point here, the table quits working because the table may go bigger than n. Okay, and let's give it a few more. Let's let it display a few more decimal places. Okay. And over here is the graph of the PDF. And this particular time I've only got it going up to 7, which is not showing the whole graph. So I need it to go out a lot farther, and I can do that by going to here and selecting data, and just make sure that I'm selecting this data here all the way down as far as we go. Or right now I'm going to go all the way down to the end here. Now by going all the way to the end, that leaves me a lot of dead space here. But you can see this, it really only goes up to 11. You can see the bars. And then really this is a step function, 0 to here. Actually stays 0, then it's a little small above 0 here, steps up here, steps up. We looked at these graphs earlier. I'm going to go ahead and change the select data to select. This time I'm selecting from the CDF line. I'm going to go all the way down to here, select all 0 to 85 or whatever it was. And it's going to get up to 1. These are errors. These are actually all be 1s from there on out. This one compares several binomial distributions where you can put in numbers that you want for n and p, which are the defining parameters, and it will figure out the mean, the variance, standard deviation, and skewness, and so forth, and you'll be able to see what's going on here. Here's the geometric distribution. Okay, and of course the geometric distribution goes on forever, with the bars being multiplied by q each time. So the bars are getting shorter and shorter each time we go out to the right, but they do go on forever. Notice we're already up fairly close to 1 here, but not all the way. I'm going to change this to, I really want percent form. I had that at one time, but I'm going to change that to just a number format. And shows several digits. So again, I could change the probability of success is 0.7, for example. The probability of success is 0.3, so this is going to drop down really fast. Whereas if I make this, say, less than 1, let's say 0.4, and the other is 0.6, each bar is 60% of the one before, as far as height. Hypergeometric. In a hypergeometric, we start with a certain number of objects, in this case 40. We have a certain number of successes, in this case 12, and we're going to choose 4, and we want to count the number of successes. Okay, and that's going to be your random variable. X is counting the number of successes. Okay, but notice that since we're doing it without replacement, the probability of a success changes each time. So let's do this a little bit bigger. Let's go. Okay, so just experiment with that. And you can, by keeping this here, for example, you can change these numbers and see how that affects the distribution over here in terms of the CDF and the PDF. And negative binomials, back where we started. The Poisson you saw earlier on the page talking about this. Same unit, same section in Blackboard. And that brings us to the end of our discussion of finite probabilities. So you can find this spreadsheet under the review section in this unit in Blackboard, and you can use this to help you compute some of these probabilities or experiment to see what happens to the graphs as you change some of the parameters and what happens to the numbers in the table as well.